1945. Fred Hoyle, Thomas Gold, and Hermann Bondi thought up the same concept Einstein had abandoned. They called it the steady state model. These were the two big ideas at the time, the primeval atom and the steady state. Hoyle actually had a radio show and spoke about science in England, and one time he was on air describing the two of them when he referred to the primeval atom, saying all the matter in the universe was created in one big bang at a particular time in the remote past. The Big Bang name was born, and it stuck. We had the foundations of the Big Bang in place, and it probably sounds pretty similar to what you think the Big Bang actually is. A long time ago, everything was closer together and hotter, and then bang, the universe is born. But there was still testing to do. One thing that people are thinking about is what happens to all of the matter, the planets, humans, stars, galaxies, all of that, as they get traced back in time to the Big Bang. The physicists George Gamow and Ralph Alpher showed that as the universe contracts, it would get hot and dense, and eventually the matter would break down into a soup of protons, neutrons, electrons, and photons. So right after the Big Bang, everything was just this soup of particles. There was no empty space. It was so hot that the whole universe was basically just one big nuclear reactor. The protons and neutrons would snap together, forming the nuclei of hydrogen, helium, and lithium atoms. After about 5 minutes, everything had cooled down enough for this nuclear reactor to shut down. All of the atomic nuclei had been formed and locked into their exact proportions. Gamow and Alpha predicted that 75% of the nuclei would be hydrogen, 25% would be helium, and a tiny proportion of things like lithium would be found. Amazingly, they were right. Observations agreed with this ratio, and they didn't stop there. This team kept thinking about the early universe and their soup. 5 minutes after the Big Bang, and the soup was filled with basically three things: atomic nuclei, electrons, and photons of light created in the Big Bang. This light was continually being absorbed by the nuclei and re-emitted, flying around in the plasma because it was so hot. The soup would stay like this for 380,000 years until it had finally cooled to a nice 2,700 degrees Celsius. In that moment, everything changed. Immediately, the electrons snapped to the closest nuclei, and those photons of light were finally free to fly out through empty space. If you were there watching, it would have been a bright red glow, and ever since then, this light should have been traveling out through the universe, being stretched by space-time as the universe expands, getting redshifted so much that it should now be in the microwave end of the light spectrum, and extremely cold, around 2 Kelvin. They called it the cosmic microwave background radiation. If they wanted to once and for all prove that the Big Bang was real, they would need to find this light, and if they could do it, they would literally be taking a picture of the Big Bang. The hunt was on. By the 1940s, an astronomer named Andrew McKellar was studying clouds of alcohol in space when he measured the temperature of that empty space around the clouds. He found it to be 2.3 degrees Kelvin. So what was it? Well, he didn't know, and no one connected the dots. He was measuring the afterglow of the Big Bang and didn't even realize it. In the meantime, the steady state model was basically dead. The main problem for the Big Bang was this age problem. It predicted the universe was far too young. New data had shown that the original distance to the Andromeda Galaxy was miscalculated. It was actually over 2.5 million light years away. So using this new data, the age of the universe was predicted to be 10 to 20 billion years old. The age problem was solved. Astronomers at Princeton had set their sights on the CMB, and they were getting close. They could feel it. But someone beat them to it. Just down the streets at Bell Labs, they had detected this strange hiss in their data. Arno Penzias and Robert Wilson couldn't figure out what it was. They tried everything to remove it, but to no avail. That's when they spoke with some people from MIT, and they realized what they were looking at. It was in fact the cosmic microwave background radiation, measured at 2.7 degrees Kelvin. They received the Nobel Prize for this discovery, and the Big Bang had its crown jewel. If we could see it today, as it were, when it was first emitted, and take a picture, it would look like a red glow in the sky from every direction. The light from the Big Bang itself. And it wasn't long until they did just that. Took a picture. By 1982, NASA had approved the creation of a spacecraft that would image the entire CMB. It could sweep the sky, mapping what it looked like in every direction. The COBE satellite. And by 1990, they had all the data they needed and made their big reveal. the CMB in all of its glory. They had mapped the entire sky's contribution and had the most complete image of the CMB ever taken. Stephen Hawking declared the result the scientific discovery of the century, if not of all time. And it wasn't just beautiful, it confirmed something that scientists had suspected for decades. In physics, there's something called a black body. It's an idealized object that absorbs all light. 100% of it. All of that energy should then be re-emitted by the object in a perfectly predictable way. Its light spectrum should look like this. Depending on the temperature of the object, this shape could change, but there is always a perfect theoretical spectrum shape for the black body. They predicted that the CMB should have this signature of a perfect black body, and it did. It was the most perfect black body ever observed in history. Standing ovations, Nobel Prizes, and an accurate description of how the universe was born. So that's the end of the story, right? The universe starts with a bang and that's it. Well, not quite. There were 3 huge problems that were still left unanswered. The first is known as the horizon problem. We have since mapped the CMB to extremely high precision and measured the thermal difference across the entire sky, and it's nearly perfect. The entire signal is pretty much exactly 2.7 degrees Kelvin, no matter where you look. The problem is, there was nowhere near enough time for the temperature to pass from one side of the universe to the other and let everything come to a perfectly even temperature. Even traveling at the speed of light, there was no way that 2 points in the CMB from opposite sides of the universe could have thermalized in the 380,000 years before the CMB light was emitted. It would have literally taken trillions of years. And you might assume that the problem would be solved if the universe were just perfectly uniform right from the start. But if that were the case, we wouldn't see this abstract distribution of galaxies today. The second problem is known as the flatness problem. Space in the universe can have different degrees of curvature. The amount of curvature is given by a number called omega. If omega is 1, then space is flat. Parallel lines will stay parallel forever. If omega is less than 1, space is negatively curved. These parallel lines will diverge. And if omega is greater than 1, space is positively curved. Those very same parallel lines will converge. When we measure the curvature of space in real life, it's nearly perfectly 1. This prediction of a flat, expanding space is inherently really unstable. If there's any slight deviation from 1 in either direction, it would rapidly diverge away from that value, like a pencil balanced on its tip falling over. And since we measure it as 1 today, it must have been unimaginably close to 1 in the distant past. If omega wasn't 1, the consequences would be catastrophic. The universe could tear itself apart or collapse and destroy itself. So why is the universe so flat? The third is known as the monopole problem, and it was pointed out by particle physicists. At such high energies like those that would have been present in the early universe, a huge number of these strange particles called magnetic monopoles should have been formed. These are hypothetical isolated magnets with just one polarity, either north or south with no corresponding opposite. The problem is, we have never found even one, and they would have been so heavy that they would have prevented the universe from expanding. And beyond these problems, there was still the singularity. Most physicists felt something had to be off, that these were just artifacts of the mathematics. Einstein even called the idea that the universe started at the Big Bang singularity repugnant. By this point in our story, everything had started to come to a head. Hawking and Penrose's proof of the singularity hinged on 4 assumptions. Gravity is always attractive, the universe has 3 space dimensions and 1 time dimension, time travel into the past is impossible, and Einstein's theory of general relativity describes the evolution of the universe at all scales. And now, every single one of them is in doubt, especially the 4th. We know that GR has some big problems when it comes to those interactions where it disagrees with quantum mechanics. Both Hawking and Penrose have disavowed many of these assumptions. Their singularity proof that time started at the Big Bang had fallen apart. It's clear that we needed something more, something better than the Big Bang singularity. Our solution would come from a brilliant physicist named Alan Guth. Guth was thinking about phase transitions in ordinary physics, ice cubes turning into liquids as they melt. If you then heat it more, you get steam. These are phase transitions. But there are some strange kinds of phase transitions too. If liquid water is pure enough, it can be cooled down below the normal freezing point, delaying the phase transition in a process known as supercooling. In the Big Bang, it was thought that the universe cooled down from an infinite temperature as it expanded, but this cooling would give us the monopole problem. So what if we could delay it like we can with water? They calculated that if the cooling is delayed a bit, the monopole problem disappears. They just don't get created. The question then becomes, what does this supercooling do to the expansion rate of the universe? Well, you might think of empty space as, well, what it sounds like, just completely empty. But quantum mechanics has shown us that it really is a sea of chaotic activity. Hidden from us, there's a layer of quantum fields, each one corresponding to a specific particle. An electron field, a quark field, you get it. When there's a ripple in that field, we get the particles that make up you and I. Our electrons come from this underlying field. In this empty space, particles and antiparticles like electrons and positrons pop in and out of existence all the time, briefly moving apart before reuniting and disappearing back into the vacuum of the quantum fields. It's these quantum interactions that gives the vacuum of empty space a tiny little bit of energy. And remember, energy and mass are the same thing. So if you have enough empty space and can extract the energy from the vacuum, you can get enough mass to create you, me, or even the entire universe. Guth started to calculate how quickly the universe would expand if it were driven by the energy of this empty vacuum of space, and the rate was insane. The universe in a tiny fraction of a second would expand by at least 100 trillion times. He immediately realized that this insane period of growth would immediately fix the flatness problem. By using this period of rapid growth, the equations got flipped upside down. The value of omega, representing the curvature of the universe, was rapidly driven towards 1. No matter what shape the universe was initially in, the vacuum energy-driven expansion perfectly flattened out the universe. The flatness problem was solved. When he did this calculation, he knew he was onto something big. He wrote spectacular realization. This kind of supercooling can explain why the universe is so incredibly flat, and therefore resolve the fine-tuning paradox pointed out by Dick. The problem seemed to disappear like magic, all thanks to this period of rapid expansion. Guth named it inflation. The final problem inflation had to solve was the horizon problem, and it was actually quite simple. Since inflation grew the size of the universe by such a huge amount in way less than a fraction of a second, any 2 points that we see that were too far apart to be able to communicate and come to the same temperature in the old model would have started out much closer together. This gives them time for the photons to go back and forth and arrive at the same temperature. That's why the CMB looks so uniform today. The horizon problem was solved too. This theory of inflation was doing magic tricks. It solved the 3 most pressing problems for the Big Bang just like that, replacing the pesky singularity in the process. And that wasn't even its biggest triumph. When we look out at the CMB, we can see these areas that have a slightly higher density. There's a little bit more of that primordial soup here than in those cold spots. And since gravity always pulls more matter towards these overdense regions, these little variations explode over billions of years thanks to gravity, giving us the cosmic web of galaxies and structure that we see today. If the CMB were perfectly uniform, the universe would have no galaxies at all. Inflation is driven by the quantum inflation field, and these fields have built-in inherent quantum fluctuations thanks to the uncertainty principle. These quantum fluctuations get frozen into the plasma as the expansion slows down, giving us the variation that we see today. If it weren't for these quantum fluctuations during inflation, there would be no galaxies or structure in the universe today. Combining all of these ideas, we can finally piece together a complete view of what actually banged during the Big Bang. We start with empty space. No matter or light, nothing at all. But our empty space is filled with an underlying field, the inflationary field. This field